Okay, people did well with the first few questions, but let's go over them quickly. If y equals 4x squared plus 7x plus 3 is represented by the column vector 4, 7, 3, then what does this column vector represent? Well, you can read the solution, but you should ignore that if you haven't seen this before. Well, how do the numbers here relate to the numbers you see here? The 4 is in front of x squared, the 7 is in front of x, the 3 is out here by itself, and the three terms are added. So that we would expect that the negative 2 would go in front of x squared, the 3 would go in front of x, and the 5 would go out here by itself, and these terms would be added. So we have negative 2x squared plus 3x plus 5. Now we know that this is a quadratic polynomial, at least I hope we know this because we've all been through calculus, meaning we should have known pre-calculus. I'm not sure that's always true, but usually is. Okay, so this is a quadratic function. It's got a parabolic graph. You can find the minimum of this by setting the derivative equal to 0. You can do all kinds of things with it. So we have a second-degree polynomial with its parabolic graph. So any three numbers in a column here will give us, if we follow the same representation rule, a quadratic polynomial, which again is a third-degree equation, second-degree, degree 2 polynomial, giving us a parabolic graph if we want to look at the graph. Okay, well, and then the function y equal 2x squared minus 5x plus 1, well, that's clearly represented then by the vector where the 2 is first, the negative 5, and then the 1. Column vector 2, negative 5, 1. Now, we could add any two of these, okay? If we add two of these, do we get a quadratic polynomial? Well, sure we do. We're going to get something times x squared, something times x, and some number out there. The same as if we added the two corresponding column vectors. So the column vectors, addition of the column vectors, represents addition of the two functions. If I wanted to multiply this function by 3, well, if I multiplied by 3, I'd have to distribute the multiplication. I'd get 12x squared plus 21x plus 9. Well, if I multiply this column vector by 3, I've got to multiply every component by 3. I'm going to get 12, 21, 9. I'm still going to get a representation of the same thing I'd get if I multiplied this function by 3. So we are beginning to suspect that these functions constitute a vector space because every one of these functions can be represented by a column vector. We just have to check a few of the properties, okay, and we're going to get to that. Okay, but I want to jump right to an application where y equals x squared is represented by the vector 1, 0, 0. Of course it is. Y equals x, of course, is represented by 0, 1, 0, and y equals 1 to be represented by 0, 0, 1. And now we write an equation that represents a question. The question being, can I combine three vectors to get some other given vector? And we'll deal with that in the next video. But we're going to treat this now as a vector space, and then we're going to come back and look at some of the properties of vector spaces to verify that they actually hold for this set of polynomials.